All right. So, good morning. So the topic of today is probabilistic classification. So let's start by linking it to what we have been doing previously in this course. So basically, the first 2/3 of the course focused on search and then, different variants of search when there was some uncertainty, when there was an adversary playing against us, when there was chance, or when there were uncertain outcomes of actions. So this was the Markov decision processes, and eventually we made it even more complicated because the agent was not given a model, but instead had to basically learn what to do just by trying it out in the environment and seeing what happens. So all that was assuming that the states in which the agent is were known. Okay, so the situation on the chessboard, or even in the reinforcement learning, in the grid or in the maze, the agent was in a particular spot, and that was the state S, and that was directly observable. So directly observable means that you don't have to perceive and then sort of decode it from some sensory input. You just know this is state S1, let's say, right? Or it's the coordinate on the grid or something like that. And so in the last block of the course, the last 3 lectures, we will make it, let's say, even more complicated and also more realistic, because we will introduce perception. So we will use sensory features, and those will be in some way linked to the actual state. So that would be basically a hidden state because it's not directly observable anymore. So that is the additional part. Now, how to map the features onto the states can be done in different ways, and we will look at different classifiers or different mappings from the percepts from the features to the states. So the sensors may have some features. So, for example, in an image, this could be I don't know, edges or something, because usually the raw sensory input is basically too high dimensional and not informative enough to be useful. So usually we use some features. Okay, and we will learn today. We do first a recap of probability, and then we do Bayesian classification and Bayesian decision making. We will introduce the Base Theorem. Which is really basic rule of probability that is very useful in this context. Later on, we will also look at other classifiers, but that will not be in today's lecture. Today, we will basically look at probabilistic or Bayesian classification and decision making, and this will also turn out that that's sort of the best you can do if you have the relevant information. Okay, so we start with some recap of probability. So let's do I'll jump a little bit. So these kind of rules, like the sum rule of probability, what is marginal probability, and what is the Base theorem. Are you familiar with that, Lukáš, Eliza? Have you? Let's start the poll. So if you are familiar with these basic probability concepts, you can vote yes. No. Okay. So, let's publish the. So you didn't have any probability in any course that you were enrolled in, Eliza, or just some of it. Math, right? Not okay. Well, it's actually math. It's not so complicated math. In any case, I'll do a recap now, and on our webpage at the lecture section for today, I also put an additional link. There is also a lecture on by Berkeley on the probability recap. So if this is too fast today, I invite you to also watch that lecture. Okay. You didn't hear anything. Okay, is it better now? Okay. Yes, I was just saying that. Well, of course, there are abundant materials on the internet, but specifically also there is one lecture from the Berkeley course dedicated to the probability recap. So if you look at our web pages and today's lecture, I also added a link to the video of from Berkeley where they do the recap of this basic probability concepts, which are really going to be needed, and they are going to be useful for you, I guess, in many things that you will do later. So okay, so wonderful. Example is picking fruits. So which is from a book, which is this one. And okay, let me share the webcam just for a second. So it's from this book, okay, which is called Pattern Classification by Duda, Hart, and Stork. So we will be using some materials from that for the last 3 lectures, but it's not really necessary to that you get that book. But just that we for this part of the course we're referring to other materials. Okay, so we've got 2 boxes. And we will, in the red box, there is 6 oranges and 2 apples. In the blue box, there is 3 apples and 1 orange. And now you pick a box at, well, not at random. So you have some way of picking the box. And then in 40% of the cases, it's the red box that you pick. And then you pick a fruit at random. So you can't see the fruit. So imagine you just put your hand inside and you don't see what is inside, and you just put the fruit. You cannot do any haptic exploration either. You just grab the first thing that is there and you take it out, and that's going to be either an apple or an orange. Now, and we can ask different questions. For example, what is the overall probability that the selection procedure will pick an apple? Or given that we have chosen an orange, what is the probability that it was from the blue box? And this will, the concepts of probability that we introduced today will allow us to answer exactly these types of questions. Okay. So first quiz. So still the same thing, same boxes, and red boxes picked in 40% of the cases, and then you pick a fruit at random. What is the probability that the selection procedure will pick an apple? So so try to solve this. Just use pencil and paper, and it's not too difficult. Pick only from no. No, you can. It's really just an illustrative drawing. No, you can. There is an equal chance of getting anything of that box. Okay, not from the top. No. So yeah. And I should start a quiz, probably a poll. So there is A, B, C, D. Okay, so I see that Martin just joined. We're starting this lecture with a probability recap, and we're now looking at this quiz. So you have 2 boxes with fruits, a red box and a blue box. There are 6 oranges. Those are the orange ones in the red box, and 2 apples. In the blue box, there's 3 apples and 1 orange. Now you have a following procedure how you pick. So in 40% of the cases, 4 out of 10, you pick the red box for some reason, and then you pick a fruit at random. You can't see, you just grab any fruit, not from the top, from anywhere. And the question now is that with this selection procedure, you do it just once. What is the probability that you will pick an apple. So try to solve this. Okay, so I see that everybody voted. So two of you say a different value. So what kind of value is it and why? Maybe you can say it or type it to the chat. What is the value that you got? $0.21. Okay, can you put the fraction and how you arrived at it? Yeah, try to stick with the fractions because then we can sort of better see. And yeah, perhaps just a little, the little calculation how you arrived at that. So red box 0.4, then times 0.25. Lukasz is writing. All right, because there are 2 out of 8. Wait, but why would you have 0.25 for the apple in the blue box? There are 3 apples and 1 orange. I see. Yeah, so I guess it's that Lukasz made just this mistake. Yeah, so okay, I'll write down how I think it should be done. So the correct answer is this one. Oh, I need to switch on the pencil. So this is the correct answer. Yes, wonderful. So everybody knows. Okay, but so how do you arrive at this? So let's introduce also the notation that we will be needing. Okay, so we write. We have so let's say we have boxes. Okay, and box can be either red or blue, and we have fruits, and they can be apples or oranges. Okay, we usually use these capital letters for variables and the small letters for instantiations for actual values of those variables. Okay, now so probability that box is red is 0.4. Probability that box is blue is 0.6. And now how do we calculate the probability that the fruit is an apple? We do. So actually this is the probability of, so we will now use the conditional probability notation, but actually you got it right, just, we're using common sense. So this is the probability of an apple, given that I picked the red box, times the probability of picking the red box, which is also what Lukáš wrote. So this is the 0.4, and this is 2 out of 8. Okay, so because there are 2 apples in the red box. Okay, and then there is the other case. So if I happen to pick the blue box, then I have probability of now let's see if I can remove the poll, but I don't know how. Okay, probability of an apple given the blue box times the probability of the blue box. So it's plus 3 out of 4, 3 apples in the blue box, times 6 out of 10, which is, the probability of picking the blue box. And that gives you the 11 over 20. Okay, so that's quite simple. Is everything clear with this example? After, since you eventually everybody got it right, this seems that it's fine. Okay, so moving on. Okay, so next quiz, ABCD. Oh, Elisa is typing something. Let's wait for that. Can put subtitles. So Elisa is asking, is there a way I can put subtitles in direct in Brute? You mean like subtitles of my speech, that there will be some speech to text? Okay, that I'm not sure, that probably we don't have that, I think. Just to check how the others are hearing. So is everybody still hearing me okay? Okay, so Elisa has problems. Okay. No, Elisa, I'm afraid that, we cannot easily make, subtitles. The only thing I can offer is that, after a lecture, I always upload the slides with, with the teacher's notes, and there you have basically a lot of information. So basically a lot from what I'm actually saying. So yeah, so that's pretty much what I can offer here. Okay, so next quiz is here, ABCD. So try to work on this one, and now there is a different question. Given that we have chosen an orange, what is the probability that it was from the blue box? So this one is more tricky. It's a bit counterintuitive because you sort of start from the end.
Yeah, it seems his phone ringed and he probably got up to answer, so I guess that's why you don't hear anything.
Sorry, I was not hearing for a second. Philip, you were saying something?
I was just saying that you probably weren't here, and that's why there was a silence.
Right. Yeah. Sorry about that. Right. So, yeah. So we have the new quiz, and yeah, as I said, it sort of starts from the other end. Okay. I see that 3 of you have already put your answer there. Okay, so this one is indeed a bit more tricky, and it will basically require you to use the base rule. Okay, everybody answered now. So 3 of you said different value. 1 of you put a C, and indeed I think it's a C, but it is a bit tricky. So let's go through that. So what I want to get is the probability of blue box, given that, so that's this conditional probability notation, that I got an orange. Now we will see this base rule in practice. We will then, later we will also look at the formula, but that's the really key formula for what we will be doing. It's called the Base Theorem. So we don't have this directly available, but we have sort of the opposite available, which is the probability of orange, given that the box was blue, and then times the probability of blue box divided by the probability of orange. And so this is the Base theorem applied to this case. And from there we can get our answer. Okay. Now the probability of blue box, that is easy, right? So that is the 0.6. Now the probability of orange, given that the box was blue, is also easy. So that's 1/4. Okay. Now the probability of orange can be the probability of orange. Then we can basically count all the oranges. So there are 7 of them. Out of how many fruits in total? 8 plus 4 out of 12. Okay, so let's see if that works out. So we have 1/4 times 6/10. That would be divided by 7/12. So that's like times 12/7. So let's see what we can get out of that. So, okay, let's make a 5 out of this and a 6 out of this. So this will give us, and then we can make a 2 out of this and 3 out of this. Sorry for the math. So that would give us 1/2 times 3/5 times 6/7. So that will give us 18 over wait, but this doesn't look right. Okay, so maybe we made a shortcut, and the probability of orange cannot be taken just like this. So instead, we have to consider the two cases separately. So the probability of orange would be equal to, okay, I'll have to start anew, so let me clear this. Okay, let's save some space here. So the probability of blue given orange is the probability of orange given blue box times probability of blue box. So these are clear. Now, probability of orange and this PO, we have to consider the two cases. Is the probability of orange given that the box was blue times the probability of blue box plus the other case, like what we were doing before. So that's actually from the first quiz. Okay, so given red box, then well, it's the complement of that. Okay, so so before we had the probability of apple, and that was 11 over 12, right? Now, so what the very basic rule of probability is that the probabilities sum up to 1. So we have here the probability of orange, which is the other case. So we could bring in all the numbers and get the result. Alternatively, the probability of orange is 1 minus the probability of apple, and then it's 9 over 20. So let's try again. So we would have the probability of orange given that the box was blue, which is 1 over 4 times the probability of the blue box, which is the 6 over 10, times the probability, so divided by the probability of orange, or times the the reciprocal value of that. So that would be 20 over 9. Okay, so let's see what we can get from this. So if we divide this by 10, you get a 2, you get a 1. So this would be the numerator would be 12 over 36, which is 1/3. Okay, here we go. Okay, so this is the correct answer. Yeah, so this one is a little more tricky, and this is a bit harder to solve by common sense. Basically, you could, but yeah, the Base theorem comes handy. Is this clear? Okay, yeah, so let's move on. Well, that's wonderful. Okay, so yeah, so here for the formal notation, so we now have the sort of the motivation. You can always imagine the fruits. I think that's quite a nice example. Okay, the notation goes as follows. So we've got random variables that we denote with capital letters. These are the values taken by the variable, which are denoted by small letters. So this is a joint probability. So you can imagine basically here is a comma. You can also imagine like an and or an intersection. So this is a probability that x takes the value of xi and y takes simultaneously the value of yi. Okay. So that's a joint probability. Yeah, this is simply that probability of x taking a value xi. Then some rule of probability is that if I have the joint probabilities and I want to obtain only the one for x, then I can basically sum over all the different values that y can take. Okay, so that's it's called marginalization. You know, it makes sense. So I know that if these two happen together, I know the individual probabilities for the pairs. And if I'm interested in just in one, then I have to sum it up over all the different values that y can take. So this is sum over the j, right? Which is, you know, what the values that y can take. The xi stays fixed because that's the probability I'm interested in, and that's called marginalization. Yeah, you can also write it like that. So you're summing over all the values that the other variable can take. Okay, conditional probability, the probability that one variable takes a value given that some other variable has already taken another value. The product rule is that the joint probability is equal to this conditional probability. So probability of, you know, x taking one value and y another value is equal to the probability that y takes that value given that x has taken the value xi times the probability that, you know, x will take the value xi. So that's yeah, basically you write it like that. Yeah, you can sort of, you know, memorize it that it's a bit like multiplication. This is a bit like divided by x, and here you multiply it. But yeah, it doesn't really apply like that. But basically, this is the rule that links conditional probability and joint probability. And finally, there is this important theorem, which is called Base Theorem or Base Rule. And yeah, this looks like this. Yeah, you can also derive it by using the product rule, but we will not, you know, we will not go into that. And yeah, basically, here is one conditional probability. Here is the opposite conditional probability. Here is the probability of y taking value, and this is yeah. Usually we use these kind of labels. The straight line is division. The straight line is not division. The straight line is a symbol that denotes a conditional probability. So it's probability of y given x. So, and you know, this is a shortcut, but in general, it has to be that probability that y has a value given that x already has a value fixed, right? So which is different than this. So this is that the two simultaneously independently take, you know, some values, whereas this is I already fix one. So that means I already fixed the box from which I'm taking the fruits, and now you tell me what is the probability of an apple, which is a different thing than asking what is the probability that you know, the box and the fruit will happen simultaneously. So it's a sort of sequence in time. Mm-hmm. Yeah, so yeah, there are these labels that help you to give some semantics to the Base theorem. So this one is denoted as likelihood. This one as a prior, which is, we will see when we, you know, look at the classification example why this makes sort of sense. This one can be denoted as evidence, and this one is the posterior. Okay, it's probably better if we then, yeah, we will look at some classification example, and then there it would make more sense. And then finally there is the independence. So yeah, anybody knows the rule there? You know, what applies if two variables are independent? What applies for their probabilities? So if I want to write p x y is equal to something, what would that be if they are independent? So that means, you know, no matter what happens to x, you know, then it doesn't affect, you know, my choice of y. So clearly the example with boxes as fruits is not the case, because if I choose the box, then it affects the probability of choosing the fruit. But if imagine in both boxes you had exactly the same fruits, then, you know, the probability of choosing a box and choosing a fruit would be the same. So yeah, so there is a basic rule that the joint probability of two independent variables is equal to the product of the individual probabilities. But this applies only if they are independent, right? So you can invent some examples like the probability that it will rain and the probability that we will finish this lecture on time. They seem like two independent events. So we can simply multiply, and this will be the joint probability that it will, let's say, not rain and we will not finish the lecture on time, okay? But, probability that we will spend another 10 minutes on this slide and that we will finish the lecture on time is clearly not independent. So then this would not be possible to this would not hold, okay? Right. Okay, so here, if I manage, there is an exercise where everybody can draw. The question is, how do I make this possible? Philip, do you know how to do that? Here, turn multi-user whiteboard on. Okay, so now you have a chance to draw everybody on the screen and connect what do you think what is the posterior in case of the fruits and boxes, what is the likelihood, what is the prior, and what is evidence. So I see only the cursor of Tejas so far. Is it technically working for everybody to be able to draw, or are you just thinking? Right, okay. So nobody wants to try? Okay, let's see. Let's wait for Lucas, or maybe Martin can also try. So okay, let's give you some hints. So the likelihood is the one where basically, so the likelihood and the posterior are the two conditional probabilities. Now the likelihood is the one that sort of follows the sort of intuitive sequence, so that's the sort of easier one typically. So in this case, it's this one. So the probability that I know the box, because I'm picking first the box and then the fruit. Now, given that I have picked the box, what is the likelihood or what is the probability of getting a particular fruit? that is the likelihood in this case. Okay, and that will also be, important, let's say, in the classification examples. You have some features, and then you want to, let's say, guess what class is it. Now, the posterior is the other one, so that's this one. It's the opposite. That's kind of the more difficult one, where you have to use the Bayes rule to get it usually. So that is what is the probability that it was a particular box given that I picked an apple or an orange. Okay. And the prior is, again, you start sort of from what you do first. First you pick a box. So the probability of a box is a prior, and then evidence is the probability of the different fruits being picked there. Okay. Yeah, so these are sort of conventions, and yeah, it may help to know the names, but you have to find your own sort of reasoning behind it, such that it helps you, or your own sort of rationale. Okay, now there are some examples where people like doctors or judges, they cannot apply probability correctly, and in fact, like common sense application of probability is often wrong. Okay, and it's not easy, and it can also have important consequences. So let's do these two motivation examples, but we probably have to catch up here. So I'll go through them rather quickly. So we will not do this quiz, but so imagine this example: a doctor calls, your HIV test is positive, so HIV is AIDS, and that almost certainly will die in 10 years. I'm sorry, and then the insurance company doesn't want to insure a married couple. So these are real world examples. Okay, so the doctor knows that the HIV test is falsely positive only in one case out of 1,000. So now the question is, what is the probability that the man is infected, right? And so the doctor, what he thought is that the probability that the man is infected is this, that it's almost certain, right? And now, in fact, this was wrong, and let's quickly see why that was wrong. So what the doctor was using is that the probability of positive test given that the person is healthy is only 1 over 1,000. Okay, and that's basically how it's similar with COVID tests. So that's basically that's how the test rating basically is. Okay, but what was actually important was the probability. So this would be the likelihood. But what is actually important, for let's say from the point of view of the insurance company or of the diagnosis, is the opposite probability, which is the posterior, which would be a probability of healthy given that the test was positive. And for this, we would have to apply the Bayes rule, and we would basically need also the prior and the evidence, right? And so for us to get these kind of things, so the correct answer would be that we would need more information, and we would need information about the incidence of that illness in the population. So given some characteristic of that couple or of that man, we could find out that, for example, it's only 1 in 10,000, in the incidence in the population. And having that, so if only 1 in 10,000 of would be HIV positive in the population, then imagine you take those 10,000 people and you test them, and given that the test has these characteristics, you would basically get 10 people out of 11 tested positively, while only 1 of them would actually be sick. And yeah, so that clearly is a different story. So in fact, given this kind of incidence in the population, which is the information that is not written up there, the probability of healthy given a positive test would then be 10/11, which is a completely different thing than 1/1000 or 999/1000. Okay, so so obviously the doctor didn't apply the Bayes rule, and with that it's not surprising, but this can completely change the change everything. Okay, so so this is just that it has implications for real life. Another example of the same kind, again, it's from real life, and it's people of I don't know if it was California probably versus Collins. You can look it up in Wikipedia, and again, based on some wrong probability reasoning, there were people sentenced to prison, and later on they revoked the case with new facts, basically claiming that the use of probability was wrong. And and then they basically let them free. But basically the idea was that there was some robbery, there was some evidence, they saw somebody that had some hair, and then they saw somebody else sitting into a car. And what they did is that they basically wrongly applied the independence assumption that the probability of let's say seeing a yellow car in general in California, let's say, is 1/10, and then this man with mustache, like 1/4 men in California wear a mustache, and then they putting all this together, all that evidence, they just multiplied it, and then the reasoning was, okay, but so the probability that all these characteristics happen together is like 1/1 million something. And then they basically, they sentenced them to prison because they said, well, this is, this cannot be. We have these two people, they are suspicious, and the probability that we find another couple that has exactly the same characteristics is like so big that it has to be them. Okay, but instead, so what they were looking at was like the probability that the randomly selected pair matches discussed characteristics. But instead, they should have been looking for the posterior, which is probability that a pair that already has these characteristics is guilty. And that would again lead on to the Base Theorem, and this would give a completely different probability, something on the order of like 40%. And only after some mathematicians looked at it, and then they revoked the trial, the trial, and then they freed them. Okay, so another example. I have the calculation in the teacher's notes, so you can look it up after the lecture, after I upload it. Okay, but we have to cover something that will be needed for the exercise, so I'm going to hurry up a little bit. Okay, this is an actual example of classification. So you may imagine a factory that processes fish or fishes. We have two different species in this case. And so there are two species, salmon and sea bass, and they have different features. So the length, the width, lightness from the camera, and so your job is, there are some feature extraction, and you should classify. So that's some kind of automatic system there. Now, so again, how do we apply the Bayes rule? So there are these two classes, and then there are features or feature vectors. They're also called attributes. Now, the optimal classification from that feature vector is the argmax. So that means I'm looking over the different classes. In this case, these are just two, S, J. S1, S2, S salmon or sea bass, given a feature vector. So, and the probability that it's a salmon given the feature vector is some number. The other probability that it's a sea bass is a different number. And I'm just taking the argmax. So I'm picking the class that is most probable, okay, which is completely logical. So this argmax just means I'm taking the class that is the most probable. And this is my posterior. So given the features, I want to get the class that is most probable. Now, why Bayes rule would be applicable here? The reason is that the other probabilities are in practice basically easier to get than this one. Okay, and we will see why. And it turns out that this is really the best you can do in classification in general if you have the right probabilities. If you have to have this one, right, if you can learn it from a lot of data, or if you can learn these three, then this is really the best you can do if you have what you need. We will see some other classifiers that are not based on probability, but they cannot do. So this is the optimal one you can have, provided that you have the probabilities there, which of course in practice may not be the case. Right. So if you are given this, now let's see why. So imagine you have the data, you have the features and you have the classes. So then there has to be an external, somebody who provides the labels, somebody who an expert says this is good salmon, this is sea bass, and then you have the features that you measured for that exemplar. And under some assumptions that that the samples are independent, so you could arrive at this probability of the class given the features just using frequentist probability. So basically taking the examples of the where for the given feature values. So this is this xi. It was a particular class. Now, in practice, this is hard, and the main reason is that the number of examples grows exponentially with the number of elements of X. So this is a vector of features, and if you imagine a camera outputting some, RGB values or whatever, it's going to have a huge dimensionality. And so the problem is going to be that you will never gather enough examples for a reasonable resolution of your features for every class and that particular value of every feature. And most of the time, the denominator will be 0, because for that particular value of of all the features in the feature vector, you will just not get any examples. So you cannot. So this is why you cannot get this in practice. Okay, so if you have an image, even if you have a 10 by 10 image, just let's say binary values, white or black, the position matters, and so the total number of unique images is still going to be huge, right? So so it grows exponentially with of course, with the resolution and with the feature vector size. Okay, so this is in practice basically the way. And that is why you have to basically turn it around and use the Base theorem. So the posterior is actually hard to get, but the likelihood is easier to get. And if the so here you see it already. So this is already using the likelihoods. Okay, so given that I have a class, what would the features likely be? That's easier to get because I can basically train, and this fish typically has these features. So that's the features given S. Okay, the probability of S is the prior, that would be the incidence of the fish. So I can also have that information available because I know from experience that from, let's say, what enters my factory, normally it's 70% sea bass. Okay. And this is just a normalization factor, which we will, learn that for classification, it's not really that crucial, how often the individual features appear, because we're really interested in this argmax, what is the most likely class. And, this is not affected by the denominator, which is the same for everyone. And now a trick, which is this naive Bayes classifier or trick, let's say, if the features are independent, which is in practice often not the case, then we can make this convenient thing that we use this independence rule of probability. And we can have that the probability of a feature given a class is the product of the probabilities for the individual dimensions of the feature vector. Okay, so if they were independent, and this is a great simplification because it allows us to basically rearrange things like that. And so imagine, let's take a concrete example. So let's have an n-dimensional feature space with let's say 8-bit values. And now, so the thing is that normally you would have 8 to the n combinations, basically, because for every element of, let's say for every pixel, I have 8 options, okay? And I have n pixels, so this would be basically what I would have to consider. Instead, if I use this independence assumption, I have just n times 8, which of course is a completely different story if I treat every feature separately. And now the question is how often that is the case. So if we talk about the pixels, do you think that pixels in images like that are next to each other are independent? And they would have, that we could treat them as their probability of taking particular values as independent. Or other examples, let's say person's height and weight. Right? I think you will do something like that during the labs, right? So they tell something else about the person. Let's say you want to guess the weight, and you want to guess. Anyway, so basically, you want to guess some characteristics of a person, or even like, I don't know, if it's if it has a higher probability of getting a particular disease. And the weight and the height, they tell a different thing, but they are clearly not independent. Okay, and same for the pixels in the image, because normally these pixels next to each other, they have a similar value. So normally this independence assumption doesn't hold, but then naive means that even though I know it's wrong, I will still use that. And it turns out that in practice, it actually often works. Okay, but you have to be aware that you're using an assumption that doesn't hold. Nevertheless, it's it's used in practice, and it has quite good results. Because it's better to do this than to deal with the curse of dimensionality, because you just cannot cope with that dimensionality normally. Okay, and I have to make sure that I cover this decision making under uncertainty. So let's move on to that. So classification is one example, but it's just you're deciding whether it was Salmon or Seabass. So there is not necessarily a cost with the two different decisions, but it could be that you have to make that decision, and those decisions have different costs. Okay. So even with the fish, it could be, for example, that the customers, if you confuse let's say have a can of sea bass and, accidentally, because of your wrong classifier, you put some salmon meat, then maybe it's fine because the customers wouldn't mind. But if you do the opposite, they will complain. So that so the classification in one direction would have, more severe consequences, so higher costs eventually associated. So let's say you get a zip code like this. Now, what is it? So where do I route it? Okay, and this may have different costs. So if I read it such that I will have to send it to a different country and then eventually back, it will have higher costs. So what is the optimal decision? So we will now look at a specific example. I apologize for this example. So it's from a textbook from the 90s, and it's not necessarily, let's say, up to today's standard. It's not really politically correct, I'd say. But, you know, let's just look at that example. So wife is coming back from work. Husband has a question. So what do I cook for dinner? And there are 3 dishes, which would be these decisions or actions in his repertoire. Nothing, or microwave frozen pizza, or some kind of delicacy. It's called General Tso's chicken here. Okay. Now, so he wants to optimize his cost, and this cost or hassle or inconvenience is basically a sum or a combination of 2 factors. It may be laborious to do, you know, some of these dishes, so that is, he regards that as cost. And at the same time, depending on the mood of his wife, you know, if she's in bad mood and he doesn't cook anything, then she will be very upset, and that would have even higher costs for him. Okay. So the loss function that quantifies these costs is here in this table. So it's a loss is a function of the state and the action he takes, the decision. So if he's in good mood and he doesn't cook anything, you know, it's sort of it's okay, right? It doesn't cost him anything. If she's in good mood and he makes that delicacy, which takes him, you know, it's a lot of effort, it has a cost of 4. Instead, if she's in bad mood and he doesn't cook anything, then the cost is even higher because she is very upset. Okay, so yeah, so this is basically how this is set up. Okay. So now the trouble is, because, you know, in this lecture we're introducing basically the perception that the states are not directly observable. The wife's state of mind is an uncertain state. Now, the observables that he does a kind of experiment before he comes home. He calls her and he says, you know, I accidentally overtaped our wedding video, and he observes the reaction. You know, if she says, okay, we keep our memories, then, you know, it's an indication she will be probably in good mood, right? Instead, if she just if there is alarming silence, then, you know, that she's likely not in a good mood. So this is basically his measurement, you know, from that phone call. And then as he collects evidence, basically as he collects, you know, data over time, he is able to come up with this joint probability distribution table of these features that he observes, and this the actual hidden state, which is the mood that she really has. Okay, so if her reaction is mild to that, you know, incident, then she's likely in good mood, right? Instead, if you know, if her reaction is not mild, then the probability that she's in a good mood. Wait, so how do I read this? So if she has, so the probability that she is in bad mood is 0, right? Instead, the probability that she's in bad mood is higher when, you know, she does this upset or alarming reaction, right? So this is what links the states and the features. Okay, so just for you to sort of be able to link it to the rest of the course. So we had this in MDPs. We had a reward or penalty, right? Which was a function of, or let's do it at the next slide, because it will allow you to better link it together. So, so the decision strategy is a rule selecting a decision for any given value of the measured attribute. So it's a bit like the, a bit like the policy, okay? You're choosing the action. Action of this decision is the same, okay? Now, here it's a function of the features, okay? Before it was directly a function of the state. We will look at this in a second, but let's first do this. So example of possible strategies. So importantly, he makes the decisions based on the features. So what on the percept rather than on the actual state, which he doesn't know. Okay. So these are examples of the strategies. So there are 3 actions, and there are 4 percepts. How many strategies do you think there are? So that would be 3 times 4. No. Three factorial times 4 factorial. Ooh, that's complicated. Okay, so in the interest of time, I tell you, it's 3 to the power of 4. So for one observation, like this one, I have 3 options. I can do nothing, or this delicacy, or pizza. So this is 3. For this next value of the feature, I have another 3 options. This I can do independently. So it's going to be like this, and it's 3 to the power of 4. Okay. Okay, now, how to define which strategy is the best and how to sort them by quality. We have to define the risk of a strategy, which is a mean expected loss value. So the risk of that strategy, I sum over all the features or the observables or the percepts and all the states. And this is the loss function, which is defined on the state and the decision. And then there is this joint probability linking the percept with the state. Okay, so in MDP and in reinforcement learning, the policy was a function of the state. However, here this state is not directly observable for the agent. Instead, he has to then decide based on the features, which is the X. So that's one difference. Okay, and then the S and X are linked through that probability. The cost, the loss, that was previously we had this reward, which was a function of state, action, and basically of the state transition. Here we associated only with the state, but it could also be a particle transition depending on the problem. But that's basically similar. The difference comes, we know that the policy is defined based on the X, so based on the features, not on the state. Okay. Now, how do we put this together? So how do we calculate? So you will do an example during the labs, I believe, using probably some coins, right? So I will not calculate that example here. You will practice during the labs. But we have 2 tables. We have the loss, and we have the joint probability distribution. And these are all the possible strategies, okay? And yeah, we have to define which one is the best. So, for one particular strategy, we can do something like policy evaluation. We could basically calculate what is the risk of a particular strategy. Now, the question is, do we need to evaluate all possible strategies? And as we saw, there is a lot of possible strategies. So this would be very, very laborious. And luckily, the answer to this is no. And I will explain that in a second. So the base optimal strategy, that is one minimizing mean risk. So it's kind of argmin over the strategies that minimizes the mean risk, right? Now, the risk is the sum of the loss function for that strategy given the percepts. Here are the states, and the percepts and the states are linked by this joint probability distribution. Okay, so this would be quite a lot of calculations, and this would be just for one strategy. So for one strategy, you would have to evaluate all that. Now, with some math tricks, you can actually take this part out, which deals with the features, because that is the same for all. And so the key observation is that you can find the optimal strategy by minimizing the risk separately for each x. Now, what does it mean? So that means that for, let's say, x mild reaction of the wife, I can figure out what is the optimal thing to do. That is the pizza or nothing, or the delicacy. Okay, and that simplifies the thing a lot. So I can find the decision for that value of x, and then I can do it separately for the other value of x, and it's kind of the same trick. Again, it deals with the dimensionality problem. So that's an important observation. Okay, so so we need to, but for, if you notice that in that formula, we don't have the p as x. Instead, we have the p as given x. Okay. But since we have this, and joint probability distribution basically has all the information, we can also obtain a table of p s given x. Would you know how to do that? So using this table to get the same table, but with s over x. So base rule, right, as usual. The s given x is the sx divided by, no, this is not base rule, for this is just the product rule, divided by px. And so we can basically, so there are two options, okay? So you can do the product rule, which is this one. Okay, so we had the product rule in the other way, right? That the p, just that you don't get lost, p s x times px was equal to p s x, like this, right? Okay, so this is just the same thing, but now we want to obtain that, so we just rearrange. And the p, s, and x, so the joint probability is something that is, those are the values in the table. Now, divided by px, how do I obtain px? So for example, for this x is mild, what would that be? Exactly, right? So px in this case would be, 0.39, 0.38. Yeah, so that would be px, right? And like this, I can get easily a new table that would be the ps given x, and I can fit it into that formula. Right. Alternatively, what I could also do is I could do the sort of calculated probability on a per column basis. So basically, the probability of, so this one, let's say S is good and X is mild, would be 0.35 over 0.39, right? Because, this makes sense. So given that X has already happened, which is this one, what is the probability of, as good as, 0.35 over that, right? Here it would be this over 0.39. So, that's kind of just, the logic of this conditional probability, because this has already happened. This is, the conditional probability, and this is, the states I'm looking for. So, either applying the product rule or just using sort of this, per column sort of common sense. So this allows you to get what you need. Okay. Moving on. Wrapping up. So given a set of possible states and decisions, there is a loss function. There is a range x of the attribute. There is the joint probability distribution. Now the strategy is a mapping from the feature space to the decisions or actions, and the risk associated with the particular strategy, you have to sum up over all the features and the states, and the loss function links states and the decisions, and the joint probability links somehow these states with the percepts. Now, the base problem goal is to find the optimal strategy. So you're minimizing the risk of a strategy, and this is how you do it. Special case is Bayesian classification, where basically the trick is that you just state would be the actual class, decision is the recognized class, and that you assign costs basically in a simple way, such that if you got the classification right, there will be no cost, and if you got the classification wrong, and there will be a cost of 1, okay? And, if you now apply the complicated formula for the decision making, and then because there are just two classes, what you just rearranging the formulas, what you get out of it is that the best classification is the argmax of probability of D given X. Okay, so applying this thing that the right classification, which is this, and the wrong classification, which is this, when S is not equal to D, sum up to 1, and fitting into here, you can eventually get this, and then that's not surprising, right? Because this is basically the likelihood. This is basically the posterior, right? So argmax, you're looking for the D, the classification that maximizes, that's how we introduced the classification problem in the beginning, that maximizes this thing, the probability of a given class given the feature vector. Okay, so we're at the end. I have some other things that I want to quickly discuss. So hopefully this will be possible in the next 5 to 10 minutes. References, there is a text by Bishop and also the Duda, Hart, and Stork that I showed you. So that's this guy. And this is, more like a sort of popular science. If you're interested in these kind of problems, this is a good book, but it's not really like a textbook for this course. Yeah, this is the textbook we've been using so far. For this part of the course, it's not really, we're not following it so closely. Yeah, so that concludes the lecture, and I will then, go back to our webpage and discuss some other things with you. Do you have questions to the lecture at this point? Yeah, we had to rush it a little bit in the second half. Everything is clear. Okay, fantastic. Wonderful. Okay. So I'm gonna share the screen. Okay, that was the wrong screen. Sorry about that. Let's try again. Okay, that's better. All right, so I'll zoom in a little bit. Okay, so today we are here. Okay, if you're uncertain about the the rules of probability, you can also watch this lecture from Berkeley that covers that in more detail. Okay. Yeah, I'll upload also my slides with notes just after the lecture. So we have 2 more lectures to go. And yeah, for next time, again, please watch the Berkeley lecture before the lecture. Here is the link. There are some additional materials on the ROC curve and a video about that by Andrew Ng, who is one of the really prominent researchers in machine learning. And yeah, there will be the lecture afterwards on this, on naive Bayesian classification, Laplace smoothing, precision recall, and ROC curve. Okay, so that's for next week. And then there will be only another lecture on the 17th, and that will conclude the semester on perceptrons pretty much. Okay. So the midterm, Philip has corrected it. You can see the results in Brood. I believe that Philip has something prepared for the lab, like one question that that was particularly problematic for you. So he will explain. And if you have specific questions to the your performance, then yeah, ask Philip. Okay, so that's for that. And yeah, as you can imagine, we will likely finish the semester in this online mode, because that's probably not worth trying anything else, even though luckily the COVID situation is improving. And we will likely also make the final exam online. And now for the final exam, there are 2 tentative dates, which are the 31st of May and the 7th of June. I don't know if they are already in course, because it's subject to some kind of whole faculty approval, how they coordinate exams from different subjects. But basically, after the semester ends, which is here, in 2 weeks on Monday morning, like we're used to, there will be the first exam date, and 1 week later there will be another possible exam date. Okay. Now, please remember that there are these conditions that you have to fulfill to be able to actually take the final exam. So you need at least 8 points for the lab assignments, and you need to submit all of the 5 bigger assignments, at least at the minimum level of functionality. And also you need to get the assessment basically based on the labs from Philip before you can actually register for the final exam. So please don't leave it to the last minute. Let's do it a couple of days in advance at latest. Talk to Philip and me, and you make sure that you have that assessment, and then you can, register for the final exam. Otherwise, you will not be able to take the exam. We will simply not, generate the test for you. Okay, so just keep that in mind. You will have basically 2 weeks after the semester ends to take care of that, to basically, get the assessment. Right, and that's it. If you have any, specific, I hope you can manage to register for one or the other exam dates, because so far we didn't plan any other, and you are not too many. So I hope that this will work for you. Any questions to that? So let me write it into the chat. So the tentative exam dates are 31st of May and 7th of June. Morning, so let's see. I guess so. I mean, so yeah, but well, normally, if you get a grade, then you get a grade. I mean, if you have a, very specific reason to retake it, then, you talk to us and probably we will allow it. Yeah, I mean, I guess that some of you, when you're doing Erasmus or something, you need to get a grade that is, above something to get your credits counted. Then yes, I think that will be possible. But I'm not guaranteeing that you will be able to do it. That we will, just for this reason, make an extra exam date for you. So in case you want to really, need a specific grade, then try to do it on the first date, because this the fact that you're not happy with the grade is not the reason that that we make another exam date. Okay, they just. Yeah, and the best advice is that really do your work in the computer labs, and you can get a lot of points during the assignments and from the quizzes, and that's really the best you can do for your final performance. Yeah, any other questions? Let's not. So the best, the easiest scheme for everybody is if you can register for the first exam date, and yeah, and then we will see what happens, and then the next exam date is already available on the 7th of June if you need to retake it. Okay, so yeah, we will see later. There might be another date, but we don't know now. And really, the best is that you prepare for the first date and you take the exam, and then fingers crossed that everybody passes. Okay, so don't start thinking about retaking from the beginning. I think yeah, just focus on preparing yourself for the first date. And yeah, it would be best if everybody can attend the first one on the 31st of May. Okay. All right then. So you will see Philip shortly at the lab, and I will see you next week. Please watch the lecture from Berkeley on naive Bayes classification and Laplace smoothing before the lecture. Okay. I wish you also a nice week. Bye-bye.